right, guys, last section of chapter 6, 6.7. We're looking to classify data sets. We're looking to write exponential functions. Then we'll see if we can do a little bit of advanced stuff with it. The three main data sets you can see right here in the middle of your screen that we're going to work to classify are linear functions, quadratic functions, exponential functions. If it's anything other than that, we're going to end up writing neither. And really, we've done this exercise, somewhere about the same time in Algebra 1. But what we do when we look at a data set, the first thing we want to always check, regardless of what the pattern is make sure the X column goes up by a consistent amount in an addition or subtraction pattern, as it were. But that going up 3 every time is good. This going up 1 every time is good. This going up 1 every time is good. Every once in a while, a textbook, a test, somewhere in the academic world, they like to try to sneak one in on you where the X's are not going up by a consistent pattern. That pretty much throws the whole thing off and just allows us to say that we can't classify the data set. The next vocabulary word is if they have constant first differences. That speaks to linear functions when there's no consistent addition or subtraction problem 1 row deep. So 4 minus 1 is 3, 3 minus 1 is 2, 2 minus 1 is 1, so on and so forth. That's an example of constant first differences. Constant second differences are what get us into the quadratic world. And you'll notice when we do the first thing where we do 3 down to 2 is minus 1, 2 to 3 is plus 1, plus 3, plus 5, that those first differences are not the same. But then if we do differences of the differences, how do we get from negative 1 to plus 1? It's plus 2. How do we get from plus 1 to plus 3? It's plus 2. How do we get from plus 3 to plus 5? It's also plus 2. That's an example of second differences being the same. Again, talking addition or subtraction patterns, this time just a second level deep, quantifies a quadratic function. And then finally, exponentials are what's known as a constant ratio. Ratio meaning multiplication division problem. So 6 times 3 gets us 18. 18 times 3 gets us 54. 54 times 3 is 62. So as we go through these problems below, I'm kind of going to be guessing, checking in these type patterns, just looking for patterns. And then we'll end up doing more with it once we get a few more skills. So determine the type of function represented by each table, and then directions, almost more of a note to myself. We will circle back to write equations for each table as well. We'll do that after the next section. So the first thing I notice is plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. So you want to check over the X. So we're good with that being a consistent pattern. I'm going to check first or second differences first. So this is plus 0.5. This is plus 1. This is plus 2. This is plus 4. This is plus 8. This is plus 16. So it can't be linear because this line's not the same. From here, this is plus 0.5. This is plus 1. This is plus 2. I really don't need to chase it out, but I'm going to anyway. So now it can't be quadratic because the second differences are not the same, which leaves us one last thing to try. And our one last thing to try being, let's see, if we times 2 here, we get 1. If we times 2 here, we get 2. If we times 2 here, times 2 here, times 2 here, times 2 here. That allows us to say that the common ratios are the same. So without a doubt, this first one is exponential. So we're basically just going to start that process all over again. So first I see, now it doesn't have to go up by 1, but I see plus 2, plus 2, plus 2, plus 2, plus 2, and plus 2. So my x column is consistently the same, so I'm good to go there. Checking first differences to see if this is linear. Minus 2, plus 2, plus 6, plus 10, plus 14, plus 18. So first differences are not the same. It cannot be linear. So we go second order D, plus 4, plus 4, plus 4, plus 4, plus 4. So I think that we've just shown that the second differences are the same. That allows us to call this quadratic. Dang it. Assume that you're starting to get the hang of this already. Does they not want to move with us? Guess not. How about that? I'll just erase quick. Thought that would stick with it, but I think that's the only one I use. Smart notebook. Just trying to hit a little law here, guys. So check the x column first. Plus 10, plus 10, plus 10. It's consistent. We'll go minus 3, minus 3, minus 3. Right away, that tells me first differences are the same. Linear. Plus 2, plus 2, plus 2. Minus 18, minus 6, minus 2 from here, plus 12, plus 4. So we've rolled out linear, we've rolled out quadratic, which means I might as well try a common ratio. So from here to here, multiplied by 1/3, multiplied by 1/3, multiplied by 1/3. So that puts us in an exponential world. Common ratio. All right, plus 3, plus 3, plus 3, plus 3, plus 3, plus 0.75, plus 3, plus 12. Obviously not linear. Plus 48, plus 192. So first difference is not the same. Plus 2.25, plus 9. So really don't even have to go any farther there. Second differences are not the same. This cannot be quadratic. So now I'll try common ratio times 4, times 4, times 4, times 4, times 4. So because this has got a common ratio, we can clearly talk to it as to being exponential. Plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. So no surprises there. This one I'm just going to skip the song and dance and show that it's multiplied by 1/2, multiplied by 1/2, multiplied by 1/2, multiplied by 1/2, by 1/2, and by 1/2. So again, common ratio, exponential. Plus 5, plus 5, plus 5, plus 5, plus 5. Let's see, minus 1, plus 4, plus 9, plus 14, plus 19. First differences can't be linear. Plus 5, plus 5, plus 5, plus 5. So second differences are the same, putting us in a quadratic world. All right. So plus 4, plus 4, plus 4, plus 4. With the x values being the same, we can carry on. Let's see. Minus 11, minus 11, minus 11, minus 11. Well, first differences are the same, so we can call that linear. And that's an idea for learning target number 1. We want to be able to go through a table and be able to use first differences, second differences, or common ratios to determine whether something's linear, quadratic, or exponential. So now let's look at the next thing down. And then we'll come back to this for the exponential tables. Okay, so our next skill is write an exponential function y equals ab dx whose graph passes through these 2 points. So what we're going to do is pull in the fact that that's x and that's y, and we're going to try to make 2 equations to essentially solve this system. So if I use this form and go 6 equals a b to the first, and then I use this to go 54 equals a b cubed. Now I want to work on ways to solve this out. What I think I'll do is take this and divide by a, make it 6 over a equals b. B to the first is just b. What that allows me to do is a little substitution over here for b. So then from there, I'll cube some of this out. So I have 216 over a cubed. Divide off some of that. So now we'll be at 54 equals 216 over a squared. I'll multiply it over 54a squared equals 216. Divide off 54 and get 4. And then be able to tell you a equals plus or minus 2. I'm not sure whether to choose between plus or minus. Let's try. I tell you, I'm going to try 2 first and see what happens. So clear out a little space here. You can always rewind the video to rewatch how I got a equals 2. And so again, on this thing, we had 6 equals a b to the first. If we plug in a 2, we are now at 6 equals 2 b to the first, which allows us to divide the 2 off because b to the first is just b. So now my prediction is that our equation should be y equals 2 times 3 to the x. That being said, let's plug these in and check. So does 6 equal 2 times 3 to the first? And that checks out. Does 54 equal 2 times 3 to the third? 3 to the third times 2, 54, and that checks out. So there's our equation. Let's see if I can get it all in one little space. It shows me I should have left more room for you on the handout. So if I use x comma y, I'll go 10 equals a b to the first. And then if I go x comma y, I'll go 40 equals a b to the third. And then we'll start along the same process that we started before. I'll make this 10 over a equals b, because b is the first. I'll sub in right here. 40 equals a times 10 over a to the third. 40 equals a times 1,000 over a cubed. Simplify a little bit, and I'll be at 40 equals 1,000 over a squared. Multiply the a squared back over. Take 1,000 divided by 40. Again, when I square root, I know normally we'd say a equals plus or minus 5. I don't have a great explanation for you right now why I'm choosing the positive, but I'm going to choose the positive and see where that takes us. And I might flip my style on C, D, E, and F and go from there. So if I go back to this original equation, I go 10 equals positive 5 times b to the first. B to the first is just b. So I'm guessing in this form, a b to the x, that my equation is going to be y equals 5 times 2 to the x. If I plug in 1 comma 10, does it work? Yes. If I plug in 40 comma 3 or 3 comma 40, does it work? Two to the third is 8 times 5 is 40. So I think I'm going to have my own question answered here down below, but we'll try it again anyway. X comma y, we go 12 equals a b squared, and then x comma y, 24 equals a b cubed. So this time what I'm going to do is instead of solving for a first like I did up here, I'm going to try to solve for b first, because for it to be an exponential equation, I know that b needs to be positive. So if I come into the plus or minus section, I can choose just the positive answer. I know b needs to be positive because for it to be a base of an exponential, it needs to be positive. If we're negative, it's no longer an exponential function. So let's try that. So I'm going to rewrite this as divide the b squared off 12 over b squared equals a. Then I'm going to solve it into, or sub it into, looks like the math's going to work out easier as well. Cancel b squared on bottom with that there. So now we're at 24 equals 12. B, 2 equals b. If we go sub it back into one of these, we'll get 12 equals a times 2 squared being 4. Holy cow. A equal to 3, so I think the equation I want is y equals 3 times 2 to the x. If we plug in 12, works. If we plug in 3 comma 24, 2 cubed is 8 times 3 is 24, works. So this one works. Yeah, so I think the generic strategy you should use on all 6 of these style problems is solve for b first, and if it tries to give you a negative answer, then throw that sucker out. I'm going to continue with that pattern here in D. So x comma y, using this, 2 equals a times b to the first, and then x comma y, 32 equals a times b cubed. Let's get a by itself here. 2 over b equals a, b to the first being b. Sub it into this bottom one. 32 equals 2 over b cubed. Cancel that b, and now we're at 32 equals 2b squared. 16 equals b squared. So here's the situation I'm talking about. When we go to square root, technically we'd say plus or minus 4 equals b. However, to be an exponential equation, negative 4 can't be the base because it would make it oscillate like we saw in section 6.1. So the only one we can choose is b, or is 4. Negative 4 is essentially an extraneous root. If we go back to one of these original equations and go 2 equals a times 4 to the first, we end up getting 1/2 for a, which makes our equation 1/2 times 4 to the x. I'll leave it to you to verify that that works for both points. All right, 2 more questions. Onward and upward. X comma y, 16 equals a, b to the second, 2 equals a, b to the fifth. Get a by itself, 16 over b squared equals a, sub into this one, 2 equals 16 over b squared, b to the fifth over 1 essentially. Cancel 2 there, cancel here. So now we're at 2 equals 16b cubed. 2 divided by 16 is 1/8. B cubed. Cube root both sides, you get 1 over 2. Sub back into original to solve, so 16 equals a times 1/2 squared. Subbing it back into this one. So now we're at 16 equals 1/4 a. Multiply both sides by 4. 16 times 4 is 64. So again, I'll leave it to you to verify that this is 64 times 1/2 to the x. A decay function for what it matters. One last one on this section, xy, xy. So 3 equals a, b to the first. 12 equals a, b squared. We'll get a by itself here, so 3 over b equals a. We'll sub it into this one. 12 equals 3 over b, b squared. Cancel and have 12 equals 3b, which means b equals 4. Sub back into an original, or our 2 equations. Another decay function. So we'll have y equals 3/4 times 4 to the x. And I'll let you sub back in the points. So at this point, what I'd like you to do is pause before going on 3 and 4 and go back up to the front page, and all of the tables that we labeled exponential, let's go back and write equations for them. Now I'm going to be a little bit of a shot in the dark because I couldn't hang on to some of this. But if I remember right, this one here was exponential. So pick whatever 2 points we want, right? Call it 1 comma 4 and call it 2 comma 8. And we can write 4 equals a, b to the first, and we can write 8 equals a, b to the second. Solve for a, sub in for a. Have 8 equals 4b, so 2 equals b. Sub it back into one of these originals. 4 equals 2a. So really what should generate this table is 2 times 2 to the x. Let's see, if we plug in a 0, we get 2 back, good, using our calculator. If we plug in 3, we get 16 back, good. If we plug in 4, we get 32 back, so that's a good equation. And some other exponentials on this front side, I believe. How about this decay function, because this was times 1/3, times 1/3, times 1/3, right? So this was an exponential. So I'm going to pull 2 comma 9 and 4 comma 3. So 9 equals a b to the second, and then I'm going to have 3 equals a b to the fourth, and see what happens. So 9 over b squared equals a. Sub in over here. Ooh, it's going to be a weird one. So we'll have this square root plus or minus the square root of 1/3. Let's go ahead and just mess with a little bit of a decimal. 1 divided by 3. So again, as established before, we can't use the negative version. That's essentially an extraneous root. So I'm going to focus on the positive version being 0.577. This isn't going to be perfect. Let's see. Nope, not going to let me. So it's not going to generate this table perfect. But if we plug it back into, say, here, we should be able to solve for a. So if I square that decimal, I'm back to 1/3. I do 9 divided by 1/3. I get a to equal 27. So y equals 27 times 0.577 to the x. I just want to see if I plug in 6 that I get 1 back. So 27 times 0.577, 35026. 2 to the power of 6. 1. Boom. It's a good equation, right? So what I want to be able to come back from you and see you do is I want to see you do this one, have an equation for that one, have an equation for that one. This is an exponential, and this is an exponential. So go ahead and take those two on and fully expect for me to ask for them in class. Good. Here was writing. Store shells, trampolines. The table shows numbers y of trampolines sold during the X year. The store has been opened. Write a function that models the data. So pulling on all the skills we had before, let's check. First of all, the x's are all going +1, +1, +1. This looks like it's going +4, +9, plus is it 11, +14, +17, +19. Does that seem right? No. 29. No. 39. 29. 29. Let's see. 96 minus 67. Sorry, my brain ain't quite working yet. +29. So it's not linear. +5. +2. It's not quadratic. Second differences are not the same. So now we need a pattern. I'm actually going to work backwards on this. So, well, kind of. 67. Imagine I wanted to do this, right? 12 times what equals 16. So I'd really do 16 divided by 12. So if I multiply this by 4/3, or I want to do 16 times what equals 25. So I do 25 divided by 16. And this is times 25/16. So our real issue here is this is not a consistent pattern. So what I would like for you to do is we need to find another way to go about this. It's probably about an exponential regression. So I tell you what we'll do there is we'll wait for me to come back. All right. So sorry about that. I'm not ready to quite attack these, at least not through video form. Do the ones above. I'll leave a second handout or a second set of problems for you to do at the completion of this video. All right. Have a great day.